Welcome back. Today I will discuss about ResNet, which is a very popular convolutional neural network model which has a very diverse application. But before starting, first we need to understand how ResNet solved deep learning's biggest problem. So let's start first talking about what is ResNet. So this is a deep neural network that solves vanishing gradient problem. Yes, if it sounds new, this vanishing gradient term to you, I will explain it. This ResNet was introduced by Microsoft Research back in 2015. And the key idea of this model is to skip connection or use shortcut to train very deep networks. So as I said, let's start with understanding what is vanishing gradient problem. So when we train any deep neural network which has many layers, for example, many convolutional neural network layer or in general neural network layers, the gradient that used to update the weight of each layer become extremely small as they propagate backward. This slows down or sometimes stop learning in early layers, making deep network hard to train. So this back propagation is followed a chain rule. Gradients are calculated using the chain rule multiplied layer by layer. If the most gradients are less than less than 1, some points, then multiplying them makes them the final gradients even smaller or tiny. And also we use activation functions like sigmoid or tanh. This function squares input into a smaller range, which is in between 0 to 1. Their gradients are even smaller, which worsen this problem. So let's understand with an example. Suppose the gradient at the layer 5 is 0.5. Similarly, gradient at layer 4 is also 0.5. So after passing through the 10 layers, we need to multiply this 0.5 10 times, which equals to 0.5 to the power 10, which is very close to 0.00097, which is almost 0. What does it result? Early layers barely update their weights. And what happened? Network stop learning. So if this early layer is not learning anything, then training the whole network is slow, even it is not training at all. Deep networks perform worse than shallow ones. So the problem of deep networks are as following, that if we go deeper network, which can give us better accuracy, not always. And the problem of deeper network is this vanishing gradient. So gradient become too small during training. Also, very deep network are harder to optimize and perform worse in terms of non-deep network or shallow network. So to find a solution of this problem, ResNet was introduced. So what it does, ResNet adds shortcut or skip connection that skip the layers. As displayed on the right side of this slide, like if the original input is X, as shown here. Then we make a connection to the you see, after the two layer, and add it here. So if the fx here, fx is the residual, that change we needed, then at this layer we are, when we are adding it, we are getting fx plus x. So the instead of learning the hx, it learns hx, which is equal to fx plus x. So basically what it does, this input x passes through layers and skip ahead, and the output equals to the fx plus x, which is easy to learn small adjustment. So this is what the proposal of ResNet. They propose it to add the input to the next, for example here, next two layer, it add that same input and skip. So this is called the skip connection in between the network layers. Now, why this skip connection works? This is a very important question. So it helps to flow, the gradient flows directly backward, no vanishing gradient. We don't need to multiply it again and again. So this helps to overcome this vanishing gradient problem. If a layer is not useful, let's say f of x equals to 0, so the output is, if you remember, the f of x plus x. That means if f of x is 0, still we have output which is equal to x. So it does not introduce, or it does not harm the network in terms of training, and making training very deep network possible. Deep means which has a more than 100 layers. Let's make a comparison between the plain network and ResNet. So in plain network, we don't have any skip connection, so no skip connection. But in ResNet, we use skip connection. So in plain network, struggle beyond 20 layers. So if it is more than 20 layers, this vanishing gradient problem make it impossible to train that network. But using the ResNet, it works more than 100 of layers and suffer from degradation. So plain network suffer from degradation due to this vanishing gradient thing, but ResNet, no degradation. There are different type of ResNet architecture. So in terms of depth, means how many layers inside that network. So there are ResNet 18, which has 18 layers. ResNet 34 means there are 34 layers. Similarly, ResNet 50, ResNet 101 or 101, ResNet 152. And when this like a deeper network, which has like more than 100 layers, it uses a bottleneck blocks, which is like one by one convolution for efficiency. And this bottleneck block is more efficient version of the residual block used in deep ResNet, like ResNet 50, 101, 152. It reduces computational while maintaining the same accuracy. So this deeper network, as I mentioned, which is 50 or 100 or more than 100, requires too many parameters. What does it makes? Like it makes the training process very slow. So it is slow training. And this bottleneck blocks, it reduce this parameter and make the training more faster. And this bottleneck blocks reduce computation using 1 by 1 convolution before and after the main 3 by 3 convolution layer. Let's see one architecture, ResNet architecture. I pick up ResNet 18, which is a smaller one and easy to understand. So this ResNet 18 model consists of 18 layers. That's why it's called 18, including convolution layer and residual block. So let's start. At the input, we have a image. Okay, then it goes through a convolution layer. Then we have a max pooling layer. I describe all these convolution layer, max pooling layer, fully connected layer, everything in a another video. I will add that video in the description as well. So here, as you see, when it passes through this max pool, it goes through 1 by 1 convolution layer, followed by 3 by 3, then again 1 by 1. This is the bottleneck I am talking about. And you see, this is the shortcut it is making. After the max pooling, you see there is an arrow going to the end of this 1 by 1 layer, convolution layer. So this is a shortcut. This is the new thing that ResNet introduced. So this is convolution 2, because we perform one convolution before that. Similar block is placed again. Okay, you see this is the convolution 3, followed by convolution 4 and 5. And finally, we have a fully connected layer. After this, we have the features of that image. So if we want to use as a classification, then we need to add a classification layer. So this is the overall block diagram of a ResNet 18. And if we go through ResNet 50 or 34 or 101, then this layer have more layers in it, which makes the more deeper network. And what are the use cases of ResNet? Obviously, it used for image classification and on the ImageNet dataset benchmark back in 2015. It is also used in object detection. For example, in faster RCN, it is used as a backbone of this faster RCNN, which means it used to extract the feature of images. Talking to the feature, ResNet can also use to extract feature in many AI tasks. So in summary, what we can say that this ResNet solves vanishing gradients problem, enables much deeper network to train and get better result out of it. And it is easy to implement. Just add a skip connection. That's it. Simple solution. ResNet make deep learning even deeper and more efficient. Before ending this video, I just want to talk one more thing about this vanishing gradient problem is that not only ResNet, there are some other solutions to solve this problem. For example, we also use ReLU activation function instead of sigmoid or tanh. So in ReLU, the gradient equals to 1 for positive input. So no multiplication shrinkage in ReLU activation. So this helps to reduce this vanishing gradient problem. Also, we use batch normalization, which normalize the output layer and smooth the gradients. And obviously, we use ResNet like network, which is skip connection, so that the shortcut led gradient flow directly to the early layers. So what are the key takeaways here? This vanishing gradient make deep network unstable and very difficult to train, but ResNet and ReLU as well as normalization layer help us to achieve a better accuracy efficiently in deep neural network. Thank you for watching. We will see you in another video.